Okay, and so, but see, we are not allowed to suspend or cancel classes during the test week. Okay, so I mean that way. So what I decided is that instead of starting any new material which requires a lot of, insights and thoughts and discussion, so we'll just what I'll do is I will solve a few examples that will give you a better idea, a much better handle to deal with problems, right? And also how to use the tools that you have learned. Okay, and I'll also sort of not go the whole length of the class. I'll leave you early. Okay, right? So all right, so we were working on this problem where a change of basis matrix has to be affected eventually. So the transformation is from R3 to R2, and there are original basis vectors that are defined in R3, and all of these basis vectors are written in terms of the elementary basis vectors, which is 1 0 0 0 1 0 and 0 0 1, and the transformation is also given to you, right? And the alpha 1, alpha 2, alpha 3 are the basis in R3, and beta 1 and beta 2 are the basis in R2. And then I define another change of basis transformation. And what we need to show is that this new transformation, new change of basis, is actually indeed a basis, right? Okay. And then we have to rewrite this in terms of the original basis vectors alpha 1, alpha 2, and alpha 3. Okay. So before we do this particular thing, I mean, let's first try to show that gamma 1, gamma 2, and gamma 3 is actually indeed a basis. Okay. All right. Now, what is so maybe I think I can erase this part. Oh no. Okay. And let's just see what happens to gamma 1, right? Now, gamma 1, as we know, is E1 minus E3. Now, what is E1 minus E3? E1 is 1, 0, 0, and E3 is 0, 0, 1, right? So this is 1, 0, and minus 1. Gamma 2 is E1 minus E2. So this is 1, 0, 0, minus 0, 1, 0. And that is 1, minus 1, 0. And gamma 3 is 2E3. So that is just 0, 0, 2. Okay. Now, clearly, these three vectors, 1, 0, minus 1, 1, minus 1, 0, and 0, 0, 2, they span R3. I mean, there is no doubt about it. Right? They span R3. But a spanning list is not necessarily a basis. So in order to show that it is a basis, what we need to do is that we have to show that these three are linearly independent. Okay. So the way to do it is pretty simple, is that you write a linear combination of these three, which is 1, 0, minus 1, plus C2, 1, minus 1, 0, plus C3, 0, 0, 2, and we set that equal to 0. All we need to show is that, what we need to show is that C1, C2, C3 They are identical 0. Now, this can be easily written in terms of simultaneous equations, right? It's pretty simple. I can rewrite this as C1 plus C2 equal to 0, and then minus C1, sorry, then C minus C2 equal to 0, and then minus C1 plus 2C3 equal to 0. Now, from this, I can clearly see that C2 equal to 0. Plug it in here, I'll get C1 equal to 0. Plug it in here, I'll get C3 equal to 0. So it's like almost trivial to see that if you solve these three equations, the only feasible solution is all of these three guys are 0. And so therefore, gamma 1, gamma 2, gamma 3 is actually a basis of R3. Okay? All right. Now, the other interesting thing is to show that you should be able to write these gamma 1, gamma 2, gamma 3, the new basis in terms of the original basis in which is alpha 1, alpha 2, and alpha 3. Okay? So how do we do that? Okay. So what we do is we write gamma 1. We have the original expression of gamma 1, which is, I mean, whatever is defined to us, right? Now, gamma 1 is E1 minus E2, right? Now, do I know what is E1? Can I express E1, E2, and E3 in terms of alpha 1, alpha 2, and alpha 3? I think I can, right? So if you check, what you can see is alpha 1 is E1 plus E3, and alpha 2 is E2 plus E3, and alpha 3 is E3, right? So what I can do is alpha 1 minus alpha 3 is nothing but E1, right? And so alpha 1 minus alpha 3 is nothing but E1, right? And alpha 3 and E3 itself is alpha 3, right? So E3 itself is alpha 3. So therefore, what I can get here is that gamma 1 is nothing but alpha 1 minus 2 alpha 2. Okay. Similarly, gamma 2, which is defined as gamma 2 is defined as E1 minus E2, E1 minus E2. Now, simply alpha 1 minus alpha 2, right? E1 minus E2, if I subtract from these two, alpha 1 minus alpha 2 is nothing but E1 minus E2, right? So it's simple and straightforward to see. Okay, and gamma 3 we already know. Gamma 3 is E3, and E3 is nothing but alpha. So we are able to express gamma 1, gamma 2, gamma 3, this new basis vector in terms of the basis vectors alpha 1, alpha 2, and alpha 3. Okay, all right. Now, remember these, there is this expression, the way these transformations are defined between alpha 1, alpha 2, alpha 3, and beta 1 and beta 2 is this. Now, what I want is, we have to write, we did this, gamma 1, gamma 2, gamma 3 in terms of alpha 1, alpha 2, alpha 3. Now, what I want to do is, I want to write a change of basis matrix between, what I want is, a change of basis matrix between gamma 1, gamma 2, gamma 3, and beta 1 and beta 2. Okay, so how do I go about doing this? Let's clear this out. There's too much stuff here anyway. Before I do that, so let's save this first. Okay, just remember that we have these results, right? And what we need to do. Okay, now what we need to do is we need to express, so basically we need a matrix, okay? We need a matrix of linear transformation like this, right? From a basis of gamma, to a basis of beta. Okay, this is what we need to do. So we need an expression in terms of gamma and beta. Okay, recall that we have the following. I mean, I think I have to write this. Recall that we have T alpha 1 equal to beta 1, T alpha 2 equal to beta 2, and T alpha 3 equal to beta 1 plus beta 2 by 2. This is what we had. We have been given this. And what we generated, what we obtained is that gamma 1, and this is what we obtained. We obtained that gamma 1 is alpha 1 minus 2 alpha 3. Gamma 2 is alpha 1 minus alpha 2, and gamma 3 is 2 alpha 2. Now, in order to cook up the matrix of the linear transformation between these two bases, what we need to do, we need to apply a linear transformation on this, right, on both sides, right? So what we need to do is the following. We need to apply a linear transformation, and we need to look at this. So T gamma 1, T gamma 2, and T gamma 3. If we don't do anything, what this will give us is a matrix of linear transformation between gamma 1 and alpha 1. But that's not what we want. We want a matrix of linear transformation between the new change of basis vectors gamma 1, gamma 2, gamma 3, and beta 1 and beta 2. So let's see what this gives us. Now, this is nothing but the transformation applied on this. And by virtue of the properties of linear transformation, we know that this is nothing but P of alpha 1 minus 2 times P of alpha 3, right? And P of gamma 2 is nothing but P of alpha 1 minus P of alpha 2. And P of gamma 3 is nothing but 2 times P of alpha 3. Good, this is good, right? Because now what we can do is, we can use our information given below to transform this into beta 1 and beta 2. Now, what we can do is, we rewrite this as P of gamma 1 is, now P of alpha 1 is what? Beta 1, and minus 2 P of alpha 3. P of alpha 3 is nothing but beta 1 plus beta 2 by 2. So beta 1 plus beta 2 by 2. Okay. P of gamma 2 is P of alpha 1, which is beta 1, minus P of alpha 2, which is beta 2. P of gamma 3 is nothing but 2 times P of alpha 3, which is nothing but beta 1 plus beta 2 by 2. Okay, all right. So further simplification, we obtain P of gamma 1, which is minus beta 2, right? P of gamma 2, which is beta 1 minus beta 2, and P of gamma 3 is beta 1 plus beta 2. That's it, right? So we know this. Now, this can be easily converted to a matrix, right? So our inputs are this, gamma 1, gamma 2, and gamma 3. I have applied the transformation on this, right? And I have obtained beta 1 and beta 2. So naturally, what I have is my change of basis matrix looks like this. Okay, so this is my change of basis matrix. Okay, all right. So this is actually how you deal with an example, and these are examples that, I mean, for small enough matrices we can do this on a piece of paper. For large enough matrices, I mean, this is easily convertible to an algorithm, right? Okay, all right. Okay, so let's save this. Okay, and let's move on to some other examples. Examples of theory that we have seen, right? Like what I wanted to do is, before I move on to right. Yeah, there is one relevant example. So where did it go? Right. Okay, this one. Okay, so what this is the following, that I give you a system of equations. Okay, all right. I give you a system of equations, and the system of equation reads like this: x1 plus 2x2 minus x3 minus x4 equal to 0. 2x1 plus 4x2 plus 2x3 minus 2x4 equal to 0. So this is a system of homogeneous equations, okay? 3x1 plus 6x2 plus x3 minus 3x4 equal to 0, okay? And x1 plus 2x2 plus 3x3 minus x4 equal to 0. See, my intention is not to solve this, but my intention is to know whether there exists unique solutions to this system of equations or whether there exists more than one solution. That's what I want to know. Okay, right? And if you did not know any theory of null spaces, rank, dimension of vector spaces, etc., linear transformation, right? So your only option would be go through this system of equations, actually solve it, right? And find out if there exists more than one solution or not. That's a tedious process, right? And I have only given you a 4 by 4. If I give you a 1000 by 1000, you can imagine the pain. Okay? So that is why the ideas of null spaces, range, linear transformations, they all come into picture, and that is how these are useful. Okay? So, I mean, what do you think? How should we approach this problem? How should we approach this problem? I want to know if there exists unique solution to the system. From whatever we have learned so far in this course, how do you think I should approach this problem? Okay, all right, very good. I'm checking nullity. Okay, how do I check nullity? I mean, what do I mean by nullity in this case? Because we are solving a system of, so our solution space is actually a system of different, I mean, the system of algebraic equations, right? So what do how do I define nullity in this case, in the context of this problem? How do I define nullity in the context of this problem? Is nothing but the basis of the, I mean, I have to figure out the solution space, right? What is the solution space? What sort of vectors are contained in the solution space, right? And so therefore, what I need to do is find the basis of the solution space, right? And of course, I also need to find the nullity, right? Nullity of what? Nullity of the solution space. I mean, the second thing follows from the first, because if you find out the basis of the solution space, you will know the nullity, right? I mean, so because you will know the dimension and etc., etc. You know that what you are doing is an R4 to R4, right? Okay. So therefore, I mean, what I do is the solution space is nothing but the null space, right? Okay. So there is this equivalence. There is this equivalence that the solution space is nothing but the null space, right? Okay. And so therefore, what this implies is that, I mean, I need to look at null of t, okay, which is nothing but t of x equal to 0, right? Now, t of x is equal to 0 implies a of x equal to 0, where a is the coefficient matrix, right? A is nothing but the coefficient matrix induced by the linear transformation t. I mean, and that we already know, right? So what is that coefficient matrix? So your matrix A is nothing but just the coefficients of it, so 1, 2, -1, -1, 2, 4, 2, -2, 3, 6, 1, -3, right? And 1, 2, 3, -1. Okay, all right. And this, so what this is, so this is your A, right? And so if this is your A, the system of equations can be written in this fashion. Okay, all right. Okay, and we know that this A is induced by T, where T goes from R4 to R4. Okay, all right. Now, what we need to do is to do some row operations, right? So reduce the matrix to a low rank. I mean, which I'm going to skip. I'll just straight away write it. So I'll just need to do some row operations. Okay, need to do some row operations. Okay, so if you do some row operations, you will see that you will be able to, reduce this matrix in the following form: 1, 2, 0. I'm just copying this: 1, 2, 0, minus 1, 0, 0, 4, 0. Okay, and the last two rows will be identically 0. Okay, this is good. Now, so this is your A, or rather what I can do is, I can easily find the rank of T from this, right? The rank of T is 2 because I have two linearly independent rows. Now, if the rank of T is 2 from the rank nullity theorem, because the dimension of your vector space is 4, from the rank nullity theorem, I know that the nullity of T is 2. Okay, all right. And I can easily find out the vectors which are also in the null space, right? This is nothing but this times x1 minus x1, x2, x3, x4, right? And I really do not need to actually find the vectors though. But if you want to find the basis of the solution space, you actually need to cook up the vectors, right? But nullity is 2, meaning, what is more important to observe here is that the nullity of T is not 0. That is more important to observe here. Okay. Now, if the nullity of T is non-zero, what do we know? If the dimension of the null space of T is non-zero, what do we know? Guys, we have proved the theorem.
It's not 1, 1.
Correct. Very good. So that means that the T itself, T is not injective, right? T is not injective. It's not a one-to-one mapping. Okay. All right. Now, if T is not a one-to-one mapping, what can we say directly about the solutions? If T is not a one-to-one map, T cannot give unique solutions. Okay. All right. There does not exist unique solutions. And this straight away comes from your, idea of functions. If function is, when you are, using a function, and when you say that a function has an inverse, right? That inverse only guarantees a unique solution to that functional equation y is equal to f of x. Otherwise, we will have a bunch of solutions, right? So this is easy to follow. So this tells us that T does not have unique solutions. We can also verify the same fact by cooking up the basis of the null space of T. Because that's easy. The basis of the null space of T, if you see, is nothing but -2, 1, 0, 0 times a vector x2, right? And there is another vector. So this is the actually, if you write the solution, 1, 0, 0, 1. You easily find these two basis vectors if you just solve this. You take this matrix, multiply with the column vector, set it equal to 0, and solve for x1, x2, x3, and x4. Okay. So this is actually your solution. Now, what you can clearly see is that I do not have explicit values assigned to x2 and x4. So this is just a linear combination of these two column vectors. Okay. If I knew explicit values of x2 and x4, like for example, 1 and -1, I would know that, these are the two solutions only. But what happens is, you can actually pick any scalar for x2, and you can pick any scalar for x4, and your one solution is -2, 1, 0, 0, 1, 0, 0, 1. Another solution is just a linear combination of this. I mean, a scalar multiple of this, like 2 times this plus 3 times this. How many such scalar multiples can you have? Plenty. Okay. Okay. So therefore, this fact is also verified. Okay. All right. So let's move on to another example. Yeah, see, I forgot something that I meant that I should have done this in class before, but I forgot. Is an example of eigenvalues and eigenvectors. Okay. So let's see. Okay, if you recall that we have talked about different types of similarity transformations, right? We said that, you know, a matrix A is similar to P inverse AP. So basically, you have to be able to find. This is just an example of a change of basis, right? This is just an example of a change of basis because we are able to find the change of basis matrix and with full rank such that its inverse exists, right? And you are able to express A in terms of this, right? I mean, now an interesting fact is that there is an interesting fact of these kind of change of basis. I mean, if you recall in the last class, I said that, why do we actually do change of basis? Because then it helps us deal, the original matrix is so complicated that we cannot actually find useful information from the original matrix. However, if we do a change of basis matrix and we find a similar matrix to the original matrix, which could be a conformal mapping, which could be just a rotation matrix or something, right? Okay, then probably and most likely handling those kind of matrices are far more easier than handling the original one, right? So there is an interesting fact is that similar matrices have identical characteristic polynomials. Okay, in other words, what it means is that the determinant of P inverse AP minus lambda I is actually determinant of A minus lambda. Okay, all right. So let's see how this makes sense. Right? I am actually not going to compute the determinant per se, but I'm just going to look at this. So this is nothing but the characteristic polynomial for this particular matrix P inverse AP, right? Okay. Now this is nothing but the characteristic polynomial of P inverse. Well, what I can do is I can write this identity matrix I as P inverse P because I know that P is an invertible matrix, right? And any invertible matrix satisfies this relation P inverse P equal to the identity matrix. Okay. Now, what I can do from this is the following: that and you know that in determinant, this is a common property of a determinant, right? I can write it this way, correct? right? Yeah. And therefore, there is another property of determinants is that I can break this up. All right. And then determinants are scalars, right? I mean, so therefore you can change the order of the determinant in any way you like. So you can and then again you can use the property of the determinant to club this guy, right? This is I. Determinant of an identity matrix is nothing but 1, and so you got what you wanted. Okay, so the characteristic of this is nothing but the characteristic polynomial of A. So if you have similar matrices, your characteristic polynomials of similar matrices are same. So what does it imply? It implies that their eigenvalues are same, right? So that means the eigenvalues of A will be the same as the eigenvalues of P inverse AP matrix. Okay, and so therefore, I mean, it's really, really simple. Okay, all right. So, I asked a similar question in test saying that if there are two matrices, AB and ABA, then their characteristic polynomials or their eigenvalues will be the same. Okay, I mean, the proof follows this similar spirit. Okay. Okay, let's see if I have another example. I do, or maybe yeah, probably, you know what? Let's call it a day for today. Okay, all right, because I know that most of you are writing exams, busy with exam week, right? So leave the class early today. So consider this a favor. Okay, all right. See you on Friday.